Now, the big question is this: how are we going to address this particular statement which says that an electron will do what to go from this particular electronic configuration to this given electronic configuration? And when we look at this particular question here, there are a couple of things we need to highlight in terms of what is happening here. What is happening is that in an atom, in this case here, when we look at the specific electronic configuration, we need to count the specific numbers that is assigned for the electrons. And in this case, we're looking at the superscripts that are above, that are listed right there. And these superscripts tells you how many electrons are in what, the letters. And what do these letters mean? These letters that are shown here are the orbitals that are in that particular atom. And these orbitals here, they have a couple of interesting characteristics that I want you all to keep in mind. Now first, let's see the total number of electrons before and what after. And so before, when we look at before, which is this particular section right here, we have a total of, adding all these numbers together, 2 plus 2 plus 6 plus 2 plus 6 plus 1, which is in total to be what, 19 electrons. And let's see by investigating after, how many electrons are there in our way to determine what is truly happening here. Now this here goes from 2 to 2, 6 to 5, 2. So in here we still have 19 electrons. So what that means is that we don't have any form of ionization happening here in terms of electrons leaving the atom or being added to that atom. But in this case, we have something that is really shown based on the later parts of the orbitals, as we observe here, and also to what we observe here. And this is where we're going to build our energy configuration for the electrons to see where they are at, and following specific rules to be able to determine what is truly happening going from before to after. Now at the left box, we're going to look at the before and see what is happening in terms of looking at the energy that is showing what the orbitals are revealing about the electrons. And on the right side, we're going to look at the aftermath of the same particular scenario. And so when we begin, we have to follow our specific energy arrangement for each of the orbitals, and this here is focusing on the n plus l rule, or the half ball rule. And this says that you have to fill electrons from the lowest energy to highest energy levels, and considering the orbitals that are at play here. So looking at both before and after, we see that we have the s orbitals that are shown right here for the energy level 1, and the next one here is our 2. For the energy level, we have s and p orbitals. Now for the s orbital, it is just above. However, what we notice is that, hey, our p orbital has a couple of degeneracy, and this degeneracy pretty much comes from the ML, or you can say the specific type of magnetic quantum number. And in here it says that we have 3 p orbitals, and so this is also applicable here for the aftermath here for the p orbitals. And then for our 3s, we have just 1 orbital. There is no degeneracy for the 3s, or in this case any s orbital. But then when we go to our p orbitals, we have degeneracy, which is the 3 orbitals that are represented right there. And finally here is our 4s orbital, and this is where the n plus l rule comes into play, that says that, hey, the 4s is considered first as top priority before determining moving on to the next one, which is the 3d orbital. And so in here 4s is going to be right above, and this is it. So we're going to label this just to be clear in terms of what orbitals they stand for in here. Now the next part is distributing the electrons, and this here we're going to be focusing on pretty much two principles. The first principle here is known as the Hund's rule, where the Hund's rule says that when you get to a particular stage you have to distribute the electrons evenly. But the other rule here is the Pauli exclusion principle, which says that for each orbital we should add opposite spin pairing on each orbital. That means you should have only two electrons, and those two electrons, they don't have the same 4 quantum number. So that's something to keep in mind here. So following that principle of the Pauli exclusion principle, we have our 1s paired up with opposite spin, and that is already taken care of for the before and after. Now for the 2s, we have those filled up and are paired, so those are taken care of. The next now is the 2p, and this is where the Hund's rule comes into play, where we have degeneracy happening right here. And so that means we have to first unpair all the electrons by adding 1 electron each before we pair up. So in here we have 1, 2, 3, and when we add the other 3 electrons, we put the opposite spin and pair them up. So 4, 5, 6. So this is taken care of, and the same thing is going to be applicable to the aftermath here, as shown right here, where we're going to unpair and then we pair them up with opposite spin, and that is perfect. So this is a combination of the Hund's rule and that of the Pauli exclusion principle, so keep that in mind. And now for the 3s here, we have the same thing as our 1s and 2s. We have the before to be the same as that of after, so this is taken care of. Now the difference is clear when we get to the 3p and the 4s in terms of what is truly happening at that later part of the orbitals. And this here shows that while before we have 6 electrons, whereby following the Hund's rule and the Pauli exclusion principle, we have this happening, and then when we pair them up we have our 6 electrons, which satisfies this number. However, for our 3p5, in this case aftermath here, we have our first unpairing the electrons 1, 2, 3, but then what happens is that we are going to only pair 2 of the orbitals, and 1 orbital it is what unpaired. But then what happened to that 1 electron? What we notice is that before, for the 4s here, we have 1 electron to be there, which is unpaired, but after we have that electron that was unpaired here to now be paired. So that means we have this happening right here. So now what is the cause of this particular change here from the 3p to now 4s? And this here all comes down to one interesting attribute that electrons have, which is enough for them to move from one level to another. They have to either absorb or emit energy. And what we notice is that in this later part here, I mean, looking at the characteristics of the energy levels, what we recognize is that for energy levels, they go from, in this case, bigger negative values to smaller negative values. And so what that means is that when we look at this bracket here and any other bracket going from this particular electron, which we're going to highlight here as, let's pick a unique color to be purple. This purple electron, what happened was that it moved from a lower energy to after, which is a higher energy, and this is where it is right now. And so when it moves from a lower energy, that means that the energy here is what? A bigger energy value, and is going to a smaller energy negative value. And so in order for you to accomplish this, you need to do something which is known as putting more positive values. So you have to put in energy in order for this electron that is here to be excited to move to a higher energy level. So this here is known as an excited electron, and this means that this electron had to what? Gain energy in order for it to move from the 3p to the 4s orbital. And so this here is what that means in this particular scenario over here. So in terms of determining how much energy that is, we can go to a couple of interesting formulas from Planck, or from Planck excitation energy. We talked about it on our previous video, but this here is pretty much what is happening here. For this number here to change from 4s1 to 4s2, and our 3p, which was initially 6, to now be down 5. So something to keep in mind in terms of how electrons behave when it comes to when light is put in or is removed from it, and in this case here is known as excitation of that atom, where the electron moves from a lower energy to a higher energy, as shown right here. So overall, I hope you found this really informative in terms of this particular topic, excitation of electrons, and I hope this here gives you an understanding on how the electronic configuration works using the quantum model, and how that impacts our understanding of how degenerate orbitals interact with each other with other orbitals that are of different energy levels. So hit a comment down below, let me know your thoughts about this. If there's any other way that you can address this particular question, please drop down in the comment section and let me know your thoughts. All the same, stay smart as always and believe in yourselves.